So hello everyone, welcome back to my YouTube channel. This is Anish Kumar and today we'll be discussing about the pumping lemma for regular languages, which is from the subject Automata theory and compiler design. So the contents that we'll be discussing about today, firstly we'll start with the introduction, then the statement, then the proof of the theorem, then an example to go with, then we'll see the advantages and where it can be useful, like we'll see the applications, and then finally we'll just conclude the session. Introduction. The pumping lemma is a fundamental theorem in formal language theory, a branch of theoretical computer science. It is used to prove that certain languages are not regular. So this theory is actually used to prove that a given language is not regular. Like if the pumping lemma theorem is true, then we get to know that the language is not true. The pumping lemma provides a way to demonstrate the limitations of regular examples by showing that for any sufficiently long string in a regular language, there must be a way to pump the string. Pump is nothing but extending the string, like repeating it again and again. Example, there's a string which goes by A, S, B, and instead of S, we can add A, B continuously. So the more we pump it, the more the number of values will be there in that certain language. So that's what we call pumping, generating additional strings that are also supposed to be in the language. Statement. Yeah, there's a theorem. So if L is a regular language, then there exists a constant n such that for every string, W belongs to L, satisfying the following conditions. For each k is greater than or equal to 0, x y to the power of k z e l. So x, y, z is actually the three parts of the given language. W is actually the language or the word whatever we have taken, and x, y, z are the three parts that will be making of that particular word. So the length of y here should be greater than 0, and the length of xy combined should be less than n. N is like a certain value or a constant that we'll be taking at the starting of the problem based on our needs. Then W may be divided into three pieces. As I told, W will be divided into three parts, x, y, and z in this case. Proof of the theorem. If L is a regular language, then some DFA M decides the language. Let P be the number of states in M. Consider any string W belongs to L with length greater than or equal to P. The characters in W will cause the machine to transition through a number of states, eventually reaching an accepting state after the last character in. Because the number of characters in W equals or exceeds the number of states in M, the machine will pass through at least one state more than once as M reads W. That is, the path that W traces through the machine has at least one loop in it. For this argument, we will use the first repeated state along the path. We will circle back around to that state for the first time before we have processed P characters. We divide our part into three parts. X is the portion of W that leads from the start state to the first occurrence of the repeated state. Y is the part of W that traces the loop back around to be repeated state. Z is the final part of W that takes us eventually to the accepting state. That is like the final state, the state that we actually want to reach at the end of the theorem. M will now accept any string of the form xy to the power of kz for k equal to or greater than 0, because such a string takes M from start to the repeated state, goes k times around the loop back to the repeated state, and then runs from the repeated state on to the accepting state. This is the example whatever we have taken. So the language whatever we have taken is a to the power of n, b to the power of n, which means the number of a's and b's will be equal in the string. This language, it will be very equal. So length of the string, which is nothing but mod of w, is n plus n. So n plus n is nothing but 2n here. We are adding n plus n because a is repeated n times and b is repeated n times. So totally n plus n will be 2n. And according to the conditions whatever we studied earlier in the theorem, 2n is greater than or equal to n. So this condition is actually true here. So break W into three parts. Only after this given condition is true, we break the given string into three different parts, x, y, and z. So here we have taken, we have split a into two parts, a to the power of n minus 1 and a to the power 1. And yeah, z is obviously b to the power of n then. So the first condition is length of y should not be null. Here y has a length of 1. So yeah, as we know, y's value here is a, and a, the length of a is once, because a is actually like uh, printed here once. So the length is 1 here, which is not equal to 0. That means the condition is true. And the combined length of x and y should be less than or equal to n. Here, the value of x is n minus 1 and the value of y is actually 1. So the simple math actually says n minus 1 will be less than or equal to n for sure, because n minus 2 it is. Yep. So the condition 3. For every k greater than or equal to 0, xy to the power of kz belongs to L. So here, as we know, a to the power of n minus 1 into a power k into b power n, k equal to 0 here. So we just take the power k here in the y um, in the y part. So we just substitute values here for a to the power of k. Instead of k, we'll be substituting different values like k equal to 0, 1, 2, and as soon like whenever we see that k is not true for any given value, then we can say that the language is not regular, even if it fails once. So here we can see that we've substituted k equal to 0 first, and then as we know, a to the power of 0 will be 1. So all we are left with is a to the power of n minus 1 into b to the power of n, which is definitely not there in the string. So this string actually accepts the value um, a, b, ABAB or AABB. It accepts such kind of values. But here, a to the power of n minus 1 and b to the power of n, here the number of a's and b's are not equal. But in the starting state, a to the power of n, b to the power of n, the number of a's and b's are equal. So that's how we can conclude that L is not a regular language here. Advantages. Language classification. The pumping lemma helps classify languages by distinguishing between regular and non-regular languages. Proof of non-regularity. One of the main applications of the pumping lemma is to prove that a specific language is not regular. By assuming that the language is regular, applying the lemma and finding a string that cannot be pumped according to the conditions, it establishes the non-regularity of the language. Development of more powerful formalisms. The recognition that certain languages are not regular motivates the exploration of more powerful language classes, such as context-free or context-sensitive languages. Algorithm insights. Analyzing the structure of languages in the context of the lemma can lead to insights into the computational complexity of language recognition and parsing. Automated analysis of regular languages. In practice, the pumping lemma can be used to automate the analysis of regular languages. Automated tools can check whether a given language satisfies the condition of the lemma, helping in the identification of regular and non-regular. Verification of compiler correctness. The pumping lemma can be applied to verify the correctness of compilers by providing a theoretical basis for understanding the limits of regular expressions in describing certain aspects of programming languages. So, conclusion. The pumping lemma for regular languages is a foundational theorem in theoretical computer science, illustrating the inherent limitations of regular languages by providing a pumping length and conditions for string decomposition. The lemma allows for proofs by contradiction, demonstrating that certain languages cannot be recognized by finite automata or expressed through regular expressions. Its significance lies in its ability to rigorously establish the boundary between regular and non-regular languages, and making it an essential concept in the study of formal languages and automata theory. So that's it for today. Hope you all liked it. Be sure to like this video and if possible share it too. Thank you.